left up.
The certification conditions are generally such that the aircraft is considered to be in the worst-case situation that could be found in operations, with or without failures. However, the rules for natural icing tests were defined a long time ago. They are extremely severe, but it is known that worst-case situations do exist. As it is impossible to find these icing conditions in the limited flight development and certification period, flight tests are performed with ice shapes on the leading edges of non-de-iced surfaces. These ice shapes simulate the maximum ice accretion that could happen in such conditions. The ice shapes are computed for each aerodynamic configuration at the usual operational speed. The differences between the shapes for the various configurations are minor. Therefore, to save time on the installation of the shapes on the aircraft and to avoid performing specific flights for each configuration with different ice shapes, it is accepted by the regulations to define and use a unique set of ice shapes for all configurations, covering the most critical situation in all cases. The ice shapes have a maximum thickness of 3 inches. They are built with a light material and installed on all non-de-iced leading edges. They are covered with sandpaper or equivalent to reproduce the granularity of the surface. The tests to be performed with these ice shapes depend on the type of aircraft. As an example, for slow airplanes with flight controls not equipped with actuators, there might be issues with the forces on the controls. The ice shapes modify the airflow, and therefore they may have an adverse effect on the handling in the entire flight domain. For large transport airplanes, the potential problems are mainly at low speeds. But in addition, further flight tests are performed to validate performances and operational flight conditions, autoland being one example. Ice shapes modify the stall conditions. There is a reduction of the stall angle of attack and of the lift coefficient. Stall tests are performed to check that the stall warning appears at the appropriate angle of attack. If necessary, adjustments are performed. Operational speeds may also be increased. On large jets with control laws incorporating stall protections, a check of their efficiency is carried out. Satisfactory results must be obtained for all the maneuvers performed for the basic tuning. To reach this target, the maximum angle of attack with high flaps deflections is sometimes slightly decreased. The regulations consider the failure case of the leading edge's de-icing system. The airplane is supposed to escape from icing conditions by an altitude or area change with a maximum accretion of 1 inch on the de-iced leading edges. All the tests mentioned previously are repeated with this failure case. 3-inch ice shapes on the non-de-iced leading edges and 1 inch on the de-iced ones. For large aircraft equipped with a hard stall protection, it has to be fully effective in all situations for at least several seconds with full backstick. In the design of the aircraft, it is important to define the leading edges that really need to be protected. This optimization may allow a significant weight reduction. Sometimes only some slats are de-iced. As an example, 1 out of 7 on the A380.